Hello, everybody. In today's lesson, I'm going to talk to you about Newton's second law of motion and how we can apply Newton's second law of motion to situations where you have objects that are accelerating. Now, before I get into my lecture notes, I do just want to quickly identify the different learning outcomes we're going to cover in this lesson from the Alberta Program of Studies. So we're going to, 1, apply Newton's second law of motion to explain, qualitatively, the relationships among net force, mass, and acceleration. 2, explain that a non-zero net force causes a change in velocity. And 3, apply Newton's laws of motion to solve algebraically linear motion problems in horizontal and vertical planes near the surface of the Earth, ignoring air resistance. Okay, so Newton's second law of motion. This is how I like to word it. So what I've said right here is when subjected to an unbalanced or a net force, maybe before I complete that statement right there, just quickly review what exactly it means to have a net or an unbalanced force. Again, I like to use the example of like two people in like a tug of war. So I'm just going to quickly like draw like a little picture of like a rope. Okay, so I have a little rope right here. Now, let's say there's people pulling on each end of the rope. So we'll say on like the right end that someone's pulling with a force of 20 newtons. On the left-hand side, somebody is pulling with a smaller force of 10 newtons. Now, obviously, the person who's pulling on the right end is pulling with a greater force than the person on the left side. So if you calculate the net force acting on this tug of rope right here, what it would be, it would be sigma F, the net force, would be equal to, well, the force on the right-hand side is towards the right, so it's positive. So you could say positive 20 newtons. The force on the left-hand side is left, therefore it's negative. So you have negative 10 newtons. And then that would be equal to a net or an unbalanced force. That is positive 10 newtons, and the positive right here means towards the right. Okay, so your unbalanced force, your tug of war winner, would be a net force that ends up being towards the right. Now, it turns out that if you have a net force towards the right, which we do in this situation right here, so like your net force, if I just drew a vector at the bottom right here, the net force would point towards the right. Now, if you have a net force towards the right, Newton's second law of motion would tell you that you are then going to move. And specifically, when I say move, I mean you're going to accelerate in that exact same direction. So my acceleration vector would also point towards the right. Now, in terms of like the actual acceleration, this is where we're going to get into a mathematical equation for Newton's second law of motion. Our acceleration varies with two specific physical quantities. So one quantity it varies with is the net force, and there's a direct relationship with the net force. I think that's pretty intuitive. So if you subject an object to like a larger net force, then your rate of acceleration is going to increase along with that net force. Now, the other variation is there's an inverse variation between acceleration and the mass. Now, maybe let's just write down an equation to represent this first, and then I'll kind of talk about that inverse relationship. So what I have right here is this is an actual statement of Newton's second law of motion. You will see a version of it on the formula sheet, although, again, I don't like to use F net. I like to use sigma F for the net force. So on the formula sheet, I think they write it down like this. A is equal to F net divided by m. Okay, so if you look at the equation right here, you can see that there is a direct relationship between net force and acceleration. So the bigger the net force, the bigger acceleration gets. And because that mass is in the denominator of the equation, there's an inverse relationship between A and M, which means that the bigger the mass is, the smaller the acceleration. I think that's also pretty intuitive. If an object, if you look at an object and it has a mass that is like much bigger than like the mass of another object, this could be like comparing, for example, like a car compared to like a little tiny box. Car has like a much larger mass. It is way more difficult to get the car to accelerate compared to a tiny like little box that you could just like push along the ground. So yeah, the bigger the mass, the more difficult it is to actually cause it to accelerate. Okay, now I like to just manipulate this equation into a format that I find a little more useful, and you'll see how this kind of like plays out once I get into the example for today's lesson and also for future lessons. If you just multiply both sides of the equation by m, you get an equation that looks like this. Sigma f is equal to mass times acceleration. It's a better starting point for how we want to actually attempt to like start solving problems where we deal with unbalanced forces and objects that are accelerating. So the application of the second law specifically is going to be to objects that are accelerating. Now, when does an object accelerate? Well, it accelerates when you have, as we mentioned on the previous slide, an unbalanced force acting on an object. Now, when an unbalanced force acts on an object, it overcomes something called the inertia of the object. Now, in terms of a definition for inertia, so inertia is basically, it's the tendency of an object just to keep doing whatever it's doing. So it could either be the tendency of an object to remain at rest, if it's at rest, or if it's moving at a constant velocity, to maintain that constant velocity. So what an unbalanced force does is an unbalanced force overcomes that inertia. So if an object, for example, is at rest and you subject it to an unbalanced force, you can make its velocity change, and therefore you can accelerate it. Or if an object is moving at a constant velocity, again, if you subject it to an unbalanced force, you can change its inertia again by changing whatever its velocity is. Now, if you look at like a chemistry definition of what mass is, I think it's like defined as like the amount of like matter or like particles that actually makes up an object, which I think is fine for like a definition in chemistry. In physics, we like to define mass a little bit more different. So the way we define mass in physics is we say mass is a measure of an object's inertia. So, which basically means like, well, what kind of objects have like larger inertia? Well, objects with larger inertia, it would be more difficult to change whatever state they're in. So if they're at rest, difficult to change it to a state where it's not at rest. So again, this is intuitive. If like you have an object that's like really, really, really heavy and it has a large mass, it would have like a very large amount of inertia. That large amount of inertia is its tendency just to keep doing what it's doing, which means that it's a lot more difficult to actually change its current state if it does have a larger mass. Now, if you go to the formula sheet and look at the section on the physics principles, the physics principle that we would apply in dealing with Newton's second law of motion would be uniformly accelerated motion or unbalanced forces. I think they write it a little bit differently on the updated formula sheet. Like the way I'm writing it right here is like unlike what it looked like originally. I think it's written like this though. I think it's physics principle number 1, and I believe they've changed it to accelerated motion. And in brackets, instead of saying unbalanced forces, they just write down the equation that indicates unbalanced forces. So I think they write down F net is not equal to 0. Yeah, if you have a net force that's not equal to 0, it means that the forces are not balanced. Okay. Now, in terms of like how to solve problems where we have objects that are accelerating, it's going to be pretty similar to like the procedure that's used for solving a problem for an object in static or dynamic equilibrium, except now we've got the acceleration component to worry about. Okay, so first things first, there's never going to be an equation on the formula sheet you can just like pull off and use to like solve a problem. We're going to have to like build our equations again. And the way we build our equations, we start off by drawing a free body diagram of the object. Now, we're also going to draw a second diagram right here to account for the fact that the object is accelerating. I call it a mass acceleration diagram, or an MAD is like the actual abbreviation for it. It's a pretty simple diagram. All we do is we draw the object, we write down the variable used to represent its mass, and then we just draw what direction the object is going to accelerate. I did put in brackets right here for each object in a system. Now, in terms of what a system is a collection of a bunch of objects. So you'll see this when we get into the example problem. If we have like a problem where we have multiple objects, we actually want to draw free body diagrams for however many key objects we have. But again, we'll just leave that until we get to the example here. Now, once you have the free body and mass acceleration diagram, we again want to derive these equations of motion. And we, once again, are going to do it in the x or horizontal direction and in the y or the vertical direction. Now, there's a small difference right here. Now, in the case of a static or a dynamic equilibrium problem, we knew that the net force acting on the object was 0. But since we have forces that are unbalanced leading to acceleration, that's not going to be equal to 0. Specifically, your net force, according to Newton's second law of motion, is mass times acceleration. So I have the net force in the x direction is mass times acceleration in the x. Similar for the y direction. The sum of the forces in the y direction, or the net force in the y direction, means the object's accelerating, and Newton's law tells me that net force is equal to mass times acceleration. We'll have two equations, and again, if you have two equations, the maximum number of unknown variables you can solve for is 2. Okay, so here's the example problem, and right away you're probably looking at it and getting like really overwhelmed. The reason the problem looks complicated is, as I mentioned, it's what I call a system. So if you actually look at the picture right here, a system, again, is just a collection of a bunch of objects. So when I look at the actual diagram, I can see M1, that's like one object. I can see M2, that's a second object. There's this rope that's connecting the two objects. And there's also this pulley that the rope is moving over top of. Okay, now, in the problem right here, we're going to assume that both the rope and the pulley have negligible mass. We're not really going to have to worry about the pulley. Later on in an AP lesson, if you are taking AP, we'll talk about how a mass with pulley can actually make this problem quite a bit more difficult. But for the time being, we're not going to worry about it. Okay, so the rope has negligible mass, the pulley has negligible mass, and we're going to assume there is no friction between the pulley and the connecting rope. Okay, so what are we going to do here? Excuse me. Draw a free body and mass acceleration diagram for each mass. That's going to be for M1 and M2. Now, B says derive an equation for the magnitude of the acceleration of the system in terms of these four variables, M1, M2, G, and FF. FF would be the magnitude of the force of friction between M1 and the surface. And then C, I then give a bunch of numerical values and then ask you to calculate the acceleration in the system and also the tension in the connecting rope. Okay, so let's start off with part A. So part A, we're going to start off by drawing free body diagrams. Now, let's do it for mass 1 to start off with. So I'll do FBD. M1. Just quickly sketch M1 here. Okay, now I'm going to draw the forces in the vertical direction first. So in the vertical direction, you have the force of gravity acting on object 1. Now, I'm going to call that FG and add a subscript here, just FG1, because I do need to clarify which mass the force of gravity is acting on. And then I'd have a normal force vector that points straight up. Now, these two vectors should be equal and opposite in magnitude. The reason being is in the y direction right here, if these forces are equal and opposite, they're balanced, which means that there is no motion in the y direction, and there isn't. The mass is just going to move horizontally. Now, in the x direction, there are two forces. If you envision yourself as that mass M1, you would feel a tension force from that rope that is pulling you towards the right. And I'm going to call that FA1. And you would also have a frictional force that is pointing towards the left. Okay, we'll just call it FF. Now, just notice right here in the free body diagram, I wanted to communicate that there is an unbalanced force. And the way I did that is I showed the FA1 vector as being larger than the force of friction vector. So again, think of it as like a tug of war in the x direction, where the applied force 1 is bigger than the force of friction, which means there's going to be a net force towards the right, which is going to make the object accelerate towards the right. Okay, now we're going to draw this other diagram called the mass acceleration diagram, or an MAD. Okay, now, MAD is you need to pick a variable to identify the mass. We're going to call this one M1, just to stay consistent with the diagram. And this object is going to accelerate towards the right. Okay, we'll just call that A1. Okay, now let's go to mass 2. So an FBE for mass 2. Okay, now this mass is going to be subjected only to vertical forces. So there's the force of gravity, of course. It's acting straight down. So you have, we're going to call it FG2. Now, the only other force acting on this one right here, because we're ignoring air resistance, is going to be the applied force from that rope. If you were M2, you would feel the tug of the rope and it'd be pulling straight up. Okay, so the tug of the rope, and we're going to call that FA2. Now, I showed again that the forces are unbalanced. FG2 is bigger than FA2, which means there's a net force that is down. A net force that is down means you're going to accelerate down, which is clearly what's going to happen when you actually release this system. Okay, so the MAD would then be, draw the mass, M2, and then just pick a vector to represent the acceleration, and we're going to call this one A2. Okay, so that's my free body mass acceleration diagram for both masses 1 and 2. Okay, now, the next question tells us we need to figure out what the system acceleration is in terms of, I think the variables M1, M2, and G and FF. Now, there's quite a bit of work involved to actually do this, but we're going to start off by writing down equations of motion. Okay, so let's go to M1 first. Okay, I'm going to assume that right is positive. And I want to find the sum of the forces in the x direction. Now, that's equal to, it's not 0 this time around because you're actually accelerating. It'd be mass times acceleration in the x direction. Okay, so that's my starting point for one of these problems. Okay, now we're going to expand the sigma fx part. Okay, so we expand the sigma fx part just like you did for an equilibrium problem. So what this means is, look at the free body diagram, look at the forces in the x direction. So there's two of them. There's FA1 and there's FF. If the force points right, put a plus sign in front of it. If it points left, put a minus sign in front of it. So this would then turn into plus FA1 minus FF is equal to, okay, now let's be more specific about the mass here. So we're going to expand the right-hand side now. So this is going to be M1 multiplied by, now acceleration's a vector, so we also have to pay attention to like what the direction is. So the direction right here is the acceleration of mass 1 is towards the right. So I'm going to put down a plus sign. So that's going to be plus A1. Okay, I'm just going to clean this up a little bit. So this would become FA1 minus FF would be equal to M1 times A1. Okay, for the time being, I'm just going to box this equation. And I'm going to call it equation number 1. Okay, so right now you can't solve for the acceleration because we have no idea what FA1 is, FA1 being the tension in the rope. Okay, now if you wanted to, you could write down a vertical equation of motion, which would be like sigma Fy is equal to 0 because the forces are balanced. That would just tell us that the normal force 1 is equal to the force of gravity 1, which is not something that's like necessary in actually solving this problem. Okay, so let's go over to M2. Okay, now this one right here only has forces in the vertical direction. So let's assume that up is positive, and I'm going to find the sum of the forces in the y direction, and that's equal to mass times acceleration in the y. Okay, and let's expand this sigma Fy part, which means look at the FBD, look at the forces in the y direction. If they point up, put a plus sign in front of it. If they point down, put a negative sign in front of it. So this one right here would be plus FA2 minus FG2 is equal to, okay, be more specific about the mass. We're going to call it M2 and then multiply by, account for the negative, account for the direction right here. This acceleration is down. So we put a negative sign in front of the acceleration. So you'd have negative A2. Now let's clean this up a little bit right here. So we'll write down FA2 minus, now Fg can be broken down a bit. Force of gravity is just m times g. But again, let's be more specific about the mass. We're going to say m2 times g. And that would be equal to negative m2 times a2. Okay, I'm going to box this right here. And I'm going to call it equation number 2. Okay, so we have two equations, but we seem to have like a really big problem right now. It seems like at the moment we have two equations and 4 variables that are unknown. We don't know FA1, we don't know FA2, we don't know A1, and we don't know what A2 is. But we can actually simplify, combine some of these variables because M1 and M2 are connected by the same rope. Okay, so I'm going to say this: since M1 and M2 are connected by the same rope, there are two things we can simplify. First things first, both of these masses, M1 and M2, are going to accelerate at the same rate, magnitude-wise. So for example, if like M2 dropped down by a meter, M1 would move to the right by a meter in the exact same amount of time, which means that you've got to have the exact same acceleration. So I can simplify this here. I'm going to say that A1 is equal to A2. And there really isn't a need to write down a subscript right here. We can just call it A. A1 is A2 is equal to A. Now, the other thing we can simplify, and now this is more complicated again if like the pulley actually does have some mass to it, but it doesn't have any mass in this problem. The tension in that connecting rope, because it's just one rope, is going to be the same. So you have FA1 is equal to FA2 is equal to FA. I mean, technically, we'd have to use Newton's third law of motion to like properly justify why this is the case, which we haven't gotten into yet. Just for the time being, we'll just make the assumption that if you have a connecting rope between two objects, and if that pulley has no mass, then every single part of the rope would experience the same amount of tension, and that's totally reasonable for the scenario where the pulley doesn't have mass. Okay, now I'm just going to rewrite the equations up here, just without the subscripts. So let's rewrite equation 1. So equation 1 would now be FA minus FF is equal to M1 times A. Maybe we'll call that equation 3 now. And the second equation we can rewrite down as FA minus M2G is equal to negative M2A. Okay, I'll box this one, and we'll call that equation number 4. Okay, so a little bit better now. So now we have two equations, and there's actually only two variables we don't know. We don't know what FA is, and we don't know what the acceleration is. Okay, so what we have now is we have a system of equations. So we have two variables, which is FA and the acceleration, and two variables, and we have two equations. So that's enough to actually solve this right here. Okay, now there are a bunch of different ways you can solve like this equation. Now, part B, what it wants me to do, and I should go back up here and just clarify this is part B. Okay, part B wants me to get an equation for acceleration. Now, in terms of what variables I'm allowed to write acceleration is, it says I can write it in terms of M1, M2, G, and FF, but I'm not allowed to write it in terms of the applied force. So what I need to do is I need to somehow eliminate the actual applied force. And I'm going to use a method of solving the system that's actually called elimination to do this. I'm not sure like whether this is taught in like Math 10C or Math 20-1. If you haven't seen this before, not a big deal. I'll do my best to explain like how you actually use the elimination method to solve it. Okay, so let's go to a new slide here just so we have more space. Okay, I'm going to rewrite these equations again. So let's write down equation 3, which is FA minus FF is equal to M1A. And then the second equation is FA minus M2G is equal to negative M2 times A. Okay, now what I'm going to do is I'm going to solve the system by eliminating FA. So I'm going to eliminate FA. And the way I'm going to do this is I'm going to take equation 3 and I'm going to subtract equation 4. Okay, so I'm going to go equation 3 minus equation 4. Okay, so I'm going to put a little horizontal line here. And I'm going to change the color of the pen. So let's go to purple. Oh. Okay, and what I want to do is I want to subtract this second equation. Now, when you subtract an equation, this negative sign right here needs to be applied to every single term. Okay? So I'm going to put the entire second equation in brackets, and that subtraction sign is then going to apply to every single term. The way you would apply the subtraction symbols with the distributive property, so this negative would apply to the FA, the negative would apply to the negative M2G, and this negative sign right here would also apply to the negative M2 times A. Okay, and then let's go back to red color. Okay, so look at this right here. FA minus FA, we can kind of just subtract, like, think about like subtracting terms like vertically, I suppose. So FA minus FA would just be 0. Okay, that's good. That's eliminated the one variable I don't want. Okay, then I'd have negative FF subtract negative M2G. Well, a negative times a negative is a positive, so that would be plus M2 times G. Now, you then have on the top, again, you can just subtract in like a vertical fashion. I mean, you got to subtract like terms that are on the same side of the equal sign. So you'd have M1A. Now subtract negative M2A. And again, a negative times a negative is going to be a positive. So you'd have positive M2A. Okay, I'm going to do a couple things right here. First things first is I don't like writing the negative term first. So on the left-hand side right here, I'm just going to change it. So it says M2G minus FF is equal to. Now, on the right-hand side, I have an A in two different terms, but to actually get the acceleration, to solve for the acceleration, I need it to be, I need to only have like one acceleration variable. So the way I'm going to get one acceleration variable is by factoring it. If you factor out the common A, you would then be left with M1 plus M2. Okay, now, to get the equation for acceleration, all you have to do is divide both sides of the equation by what's in the brackets right there. So you'd have acceleration would be equal to M2G minus the force of friction, divide by M1 plus M2. Okay, I'm going to box this equation right here. And that is the answer to part B. Okay, that's the acceleration of the system in terms of M1, M2, G, and the force of friction. Okay, now part C actually gives us numerical values to play around with. It tells us M1 is 100 kilograms, M2 is 300 kilograms, the force of friction is 100 newtons, and we want to calculate two things. First thing, the acceleration, magnitude of it. So let's just plug numbers into that equation now. Okay, so M2 is the smaller mass, so that is 300 kilograms. Multiply by G, that's just the magnitude of the acceleration due to gravity, so 9.81 meters per second squared. Subtract the force of friction. The force of friction is 1,000 newtons. Okay, divide this by M1 plus M2. M1 is 100 kilograms. Plus M2, which is 300 kilograms. Now, just a word of caution when you plug this into your calculator, because you have two terms in both the top and the bottom. I put like the numerator in its own set of brackets and the denominator in its own set of brackets. And then when we calculate this and we're going to 3 significant digits, this would then be 4.86 meters per second squared. Okay, now we also want to calculate tension. Now, it's actually, part B was a lot of work to determine what the magnitude of the acceleration was. But it turns out that like when you solve a system, like once you get one variable, it's really easy to solve for the other one. So I'm just going to go back here for a second. Yeah, let's go back to this slide. Okay, look at equations 3 and 4. Equations 3 and 4, we can use either of those equations to calculate what the applied force is. All we'd have to do in those equations is, like for equation 3, just add FF to both sides. Equation 4, add M2G to both sides of the equation. Now, this is actually a way that you can double check to make sure that you solve the system correctly. Excuse me. If you plug in the same A value into both 3 and 4, you have to get the same tension. If you don't get the same tension, it means that you either calculated A incorrectly or you did not derive it correctly. So you can use 3 or 4 to do this. Now, I'm going to pick the easier equation, the one that has like less variables in it. So I'm going to pick equation 3. So I'm going to use equation 3 to find FA. Okay, so equation 3 was FA minus FF is equal to M1 times A. Solve for FA by adding FF to both sides. That'd be FA is M1A plus the force of friction. Okay, now we can just plug numbers in. So M1, that's 100 kilograms. The acceleration is 4.86 meters per second squared, plus the force of friction value, which is given as 1,000 newtons. And that's going to give me the applied force would be equal to, you're going to have to write this in scientific notation. So we can write down 1.49 times 10 to the 3 newtons. Or if you want to, I think you can just divide by 1,000 and write it in kilonewtons. You could write down 1.49 kN. Okay, I just wanted to point out one thing before I kind of just identify like which assignment to complete. So I want to go back to the FBD MAD right here and talk about like why I do both of them. Okay, so I'm just going to pick a different color of ink right here. Okay, so what the FBD is the FBD is just a visual representation of like the sigma F part of the equation. Okay, the MAD is just a visual representation of the MA part of the equation. So really what we're doing is we're taking Newton's second law, we're representing it visually, and then from this visual picture, we're then building whatever equations we need to solve the problem. Okay, so complete the assignment called Newton's second law of motion. Thanks.